Hello, and welcome to the TI Precision Lab session on solving stability issues where there is capacitance on the amplifier's inverting node. Early in the stability series, we mentioned that stability problems can happen because of capacitance on the amplifier's output and on the inverting input. We explained how our ISO can solve stability problems in cases where capacitance is connected to the amplifier's output, but we never explained how to solve stability problems from capacitance on the inverting input. This video will cover that topic. Here are some common examples of circuits that have stability concerns because of capacitance on the inverting input. The problem is related to the interaction between the capacitance and feedback elements. Large feedback resistors and/or large input capacitance can introduce stability problems. The transimpedance amplifier is a configuration that will normally require some stability compensation. This is because the parasitic capacitance of the photodiode and the feedback resistor can be quite large. Another example is low power amplifier circuits. These can be problematic as the feedback components are normally selected to be large resistors to minimize power consumption. The last circuit shows an example where transient suppression diodes are used to protect the device. These diodes often have significant parasitic capacitance. There are many other possible circuits that can have this issue. The key point is that when you see capacitance on the inverting input or large feedback elements, you need to check stability. Here is an example of a low power op-amp paired with large feedback resistors. Running an AC sweep shows that the amplifier's gain has significant peaking near the bandwidth limit of the device. Furthermore, notice that the phase shift rapidly drops by about 180 degrees near the bandwidth limit. This kind of gain phase response is a good indicator that the circuit has stability concerns. Simulating the same circuit with the open loop test configuration is the best way to confirm phase margin. In this case, you can see that the phase margin is about 14 degrees. Notice on the gain plot that the 1/beta function increases at high frequency. This happens because the amplifier's input capacitance interacts with the feedback network. This slide shows a simplified closed-loop version of the previous circuit. The Cin capacitance represents the common mode and differential input capacitance of the amplifier. In reality, this capacitance can also include some parasitic capacitance from the PCB trace connecting the inverting input to the feedback resistors. In any case, this capacitance is in parallel with Rin. The gain of a non-inverting amplifier is normally calculated with the equation Rf over Rin plus 1. In this case, Rin is a complex impedance, so a better way to state the equation is that gain is equal to Zf over Zin plus 1. The impedance of Zin is the parallel combination of Rin and the reactance of Cin, or Xcin. Since Xcin decreases at high frequency, the impedance Zin will also decrease. When Zin decreases, gain will increase. This is why the 1/beta curve increases at high frequency. Solving the gain transfer function for poles and zeros produces a zero frequency given by the general equation at the bottom of the page. The full derivation is given at the end of this presentation. Examining the gain plot shows that the 1/beta curve intersects with the AOL curve at a rate of closure of 40 dB per decade. The slope of AOL is minus 20 dB per decade, and the slope of 1/beta is plus 20 dB per decade, so the difference is 40 dB per decade. Recall from the rate of closure rules that 40 dB per decade is unstable. Thus, this circuit is unstable because of the zero in 1/beta. This slide shows another example of this problem. In this case, the amplifier is in a gain of 11 or 20.8 dB. The feedback network has a 1 megaohm and 100 kiloohm resistor, so the overall impedance is relatively high. Finally, the amplifier input is protected with a TVS diode. The TVS diode has a significant capacitance of 1 nanofarad. The combination of relatively large impedances and a large input capacitance creates the 0 and 1 over beta as we saw previously. In this example, the 0 is at an even lower frequency, so the stability problem is even more profound. This stability problem can be corrected by adding a pole into 1 over beta. Note that the phase margin for this circuit is 13.8 degrees, so it has significant stability issues. Let's zoom into the part of the curve where 1 over beta intersects AOL and consider the impact of a pole. This slide illustrates several different placements for the pole frequency. The important point is that the pole must occur before 1 over beta intersects with AOL. The first example shows an unstable case where the pole occurs after 1 over beta intersects AOL. In this case, the rate of closure is still 40 dB per decade. The second example illustrates where the pole frequency is set at the frequency where 1 over beta intersects AOL. This case is the minimal requirement for stability. The third case illustrates where FP is set below the intersection point, and the final case illustrates where the pole frequency happens below the 0 frequency. The last two cases are both stable. Reducing the pole frequency will improve the robustness of the stability fix. In other words, the circuit will remain stable even with component and process variation. The minimally stable circuit may have some stability concerns with process variation. Besides impacting stability, the pole location will impact the closed-loop frequency response as well as the total system noise. Now let's look at a practical way to add the pole using a feedback capacitor. A feedback capacitor can be used to add a pole into the 1 over beta curve. In this example, the pole is set to a frequency where AOL and 1 over beta intersect. This is the highest frequency the pole can be set to and still solve the stability issue. The derivation of the pole frequency and the equation for minimum capacitance is derived at the end of this document. Think of the 1 over beta curve as the closed-loop gain of the amplifier. The input capacitor causes Zin to get smaller, and the feedback capacitor causes Zf to get smaller. The change of Zf will cancel the change on Zin so that the gain becomes constant. Using the equation for Cf minimum on this example gives a value of 12.6 picofarads for the feedback capacitor. The pole frequency can then be calculated with the next equation to equal 12.6 kHz. Doing the open loop analysis simulation for this circuit shows the poles and zeros as expected. Also, the phase margin is 62.8 degrees for this example, whereas it was 13.8 degrees. Thus, simply adding the feedback capacitor substantially improved stability. Now let's look at another option for the feedback capacitor. One choice for Cf is to choose it so that the pole and zero frequencies are equal. In this case, the 1 over beta curve will remain flat as the pole and zero happen at the same frequency and cancel. The calculation for this option is simple. Just make sure that Rf times Cf is equal to Rin times Cin. For this amplifier, Cf equal to 100 picofarads will set the pole and zero equal to each other. Reviewing the open loop analysis shows that 1 over beta is flat across all frequencies and the phase margin is 59 degrees. This method of balancing the pole and zero produces a robust solution compared to the minimal capacitance solution, as variation in component values should not impact stability. In the case of the minimal capacitance solution, variations in the feedback or input capacitance could make the circuit unstable. The approach is also popular because of its simplicity. Later, we will compare the bandwidth and noise for multiple feedback capacitor options. To a point, increasing Cf will improve the robustness of the stability solution. However, for large feedback capacitors, the combination of the feedback capacitor and the input capacitor presents a capacitive load to the amplifier. In this example, the pole frequency is set below the zero frequency. Doing this will cause the amplifier bandwidth to roll off after the pole until the zero cancels it. Overall, the phase margin of this circuit is 42.8 degrees. This isn't a terrible phase margin, but it is not as good as previous circuits. Ideally, we target a phase margin of 45 degrees or better for stability, and this circuit doesn't meet that criteria. Looking at the AOL curve, you can see a second pole introduced at about 10 kHz. This is what is reducing the phase margin in this example. The key point here is that arbitrarily increasing the feedback to large values isn't a good approach for stability. It is best to check stability with the open loop method. Beyond this effect, increasing CF will reduce the bandwidth and noise of the circuit. This slide provides more detail on the possibility that adding a feedback capacitor can introduce a capacitive load. In the previous slide, the input capacitance is 1 nanofarad and the feedback was selected to be 500 picofarads. Both capacitors are fairly large. The two capacitances are effectively in series with the amplifier output, so the total capacitance can be calculated using the standard rule for capacitors. In the case of series capacitors, they add using the same method as resistors in parallel. In this example, the 1 nanofarad and 500 picofarad capacitors add to a total of 333 picofarads. Depending on the amplifier, a capacitive load in this range may introduce stability problems. Keep in mind that the total capacitance in a series circuit will be less than the smallest capacitor. For this reason, if Cin is small, the total capacitive load will be small regardless of what the feedback capacitor is. This is the reason that for most amplifier configurations, making CF large does not degrade the circuit stability. This slide illustrates the closed-loop gain, noise density, and integrated RMS noise for the three different feedback cases we considered. Note that the minimum capacitance introduces noise gain peaking, which produces the highest overall noise. Setting RF times CF equal to Rn times Cin provides a relatively flat gain response and less noise than the minimal CF case. Finally, choosing the pole frequency lower than the zero will cause the gain to roll off at the pole frequency and flatten when the zero occurs. Note that this case has some gain peaking because of the capacitive loading we discussed in the previous slide. Nevertheless, setting the pole frequency to a low value limits the bandwidth and consequently reduces the noise. In general, you will see similar noise and bandwidth results for other circuit designs when adjusting the feedback level. Now we will transition to an explanation of stabilizing transimpedance amplifiers. Technically, this is just a special case of the previous discussion, but transimpedance amplifiers are a common application, so it is worthwhile to see the rules applied. A transimpedance amplifier is designed to translate an input current to an output voltage. Generally, this is done by applying the input current to the inverting input where it will flow through a feedback resistor to generate an output voltage. The most common application of the transimpedance amplifier is to convert the output current from a photodiode to a voltage. The feedback resistor value is the transimpedance gain. Thus, if a 10 microamp photodiode current is applied to a transimpedance amplifier with a 100 kiloohm resistor, the output will be the current multiplied by the feedback resistor, or 1 volt in this example. The schematic above shows a simplified equivalent model of a photodiode. The model contains a current source, junction capacitance, and leakage resistance. The current source represents the conversion of light into current by the photodiode. The junction capacitance and leakage resistance are parasitics that relate to the design of the photodiode. Notice that this example has a 70 picofarad capacitance and 150 megaohm leakage resistance. Although the photodiode capacitance will vary for different models of photodiode, 70 picofarads is a fairly typical value. Placing a 70 picofarad capacitance on the inverting amplifier input will likely cause a stability issue. This is especially true when large feedback resistors are used, and it's common to use large feedback resistors in transimpedance amplifiers. Therefore, it is a common requirement for photodiode circuits to need a feedback capacitor to counter the zero introduced by the diode junction capacitance. Here we show the AC transfer characteristic for the transimpedance amplifier. Note that the signal source is a current generator. You can see from this graph that there is significant AC gain peaking and a dramatic 180-degree phase shift at 1 MHz. This is a good indicator that the circuit has stability issues. Doing the standard open-loop stability test shows that 1 over beta has a 0 at 22.7 kHz. The 1 over beta curve intersects AOL with a rate of closure of 40 dB per decade, so the circuit is unstable. Also, the phase margin is 1.4 degrees, which indicates significant stability issues. Here we use the same relationship to find that the minimum feedback capacitance needed for stability is 1.67 picofarads. Choosing this capacitance flattens the 1 over beta curve at the point where 1 over beta intersects AOL. Using this capacitor improves the phase margin from 1.4 degrees to 51.4 degrees. Keep in mind that this is the minimum feedback capacitance required for stability. It is good practice to increase this capacitance to account for process variation and tolerance. Increasing the capacitance will decrease the system bandwidth and total RMS noise. Here we look at the transimpedance AC transfer characteristic of different feedback capacitors. The first case shows the feedback set to 0 farads. This case is unstable and has significant peaking. The other cases are all stable, and depending on the capacitance used, the bandwidth is different. The case where the feedback is set to 1.7 picofarads corresponds to the maximum bandwidth and minimum feedback capacitance allowed for a stable circuit. You can see that the transimpedance amplifier is just a specific example that follows the rules described earlier. That concludes this video. Thank you for watching. Please stay tuned to try the quiz to check your understanding of this video's content. Question 1. What is the most likely reason the circuit below is unstable? The answer is B. Capacitance on the inverting input adds a 0 and 1 over beta. Question 2. For the transimpedance circuit below, how can stability be improved? The correct answer is E, all of the above. Thank you for your time. Stay tuned for further detail on the derivations of equations used in this video. This slide shows the derivation of the poles and zeros for the non-inverting and inverting amplifier. Note that from a stability perspective, all amplifiers should be analyzed as a non-inverting amplifier. This slide shows the derivation of the special case where the pole and zero are equal to each other. This slide shows graphs that will be useful in the derivation of the equation for the minimal feedback capacitor. Note that the equation for 1 over beta uses a simplification where the quantity F over Fz squared is assumed to be much greater than 1. The goal of the derivation is to place the pole directly at the intersection of AOL and 1 over beta. This derivation has supporting graphs on the previous slide. It also uses the equations for Fz and Fp from the previous derivations. On the left half of the slide, we use the 1 over beta and AOL relationship from the previous slide. The two equations are set equal to each other and solved for the intersection frequency, Fi. On the right half of the slide, the relationships for poles and zeros are substituted into the Fi relationship. Solving this relationship gives the minimum feedback capacitance for stability.